Kia ora koutou. This video is for Ben and it's a stats hypothesis testing question from June 2021. I really like this question, but you do have to remember some stuff from AES for the second part of the question to get the normal approximation to the binomial correct. Okay, so let's just read through it. The first part is the setup. So we've got a game where a ball is thrown and it lands in one of four slots, A, B, C or D, and Raju wants to test whether the probability that the ball will land in slot A is 1/4. Now there's no suggestion that it's going to be lower or higher, so this is going to be a two-tail hypothesis test, and we just have to state the null and alternative hypotheses for Raju's test. After that, the ball actually gets thrown 100 times and it lands in slot A 15 times. So that's a binomial situation, right? N is 100. And if the null hypothesis is true, then P is going to be 0.25 or 1/4. But we're told to use a suitable approximating distribution to carry that test out at the 2% significance level. So let's set up A first, and then I want to talk a bit about why we would want to use an approximation instead of using the binomial. And then I'll talk about why that approximation needs to be the normal approximation. So in part A, if P is the probability that the ball lands in slot A, then we've got H0, the null hypothesis, is that P is equal to 1/4, and H1, P is not equal to 1/4. It was funny reading the examiner's report on this. They said that some students had written HA, but that it wasn't clear that that was an A and not an O, so they didn't get the mark. So I guess that's finally I've understood why they never write HA in Cambridge textbooks or exams. So just go with H0 and H1. So that's the first mark. So let's have a look. If we throw the ball 100 times, then we've got NP is equal to 25, and we've got large N. So this is the situation where NP is bigger than 5, and NQ is also bigger than 5. So NQ is going to be 75. What we need to have here is we're going to use a normal approx. And that's because when we've got the mean quite far away from 5, then the distribution will be, oops, I don't want that. Let's turn off ink to shape. The distribution is going to be pretty close to fitting a normal distribution. So if H0 is true, then this bar with 25 successes will be the mean, and so on. Right, now I'm drawing that bar chart to jog your memories that we're going to need to do a normal approximation, but we're going to need to use a continuity correction. Okay, so the first thing to do is to say, well, what's my approximating variable going to be? We'll call it x dash. It's going to be roughly normal, and it's going to have a mean of NP, which is 25, and its variance is going to be NP1 minus P, which is 100 times 1/4 times 3/4, which gives us 18.75, right? And we're doing this assuming that the null hypothesis is true. So what we want to do now is to see how likely is it to get this result here, or something even weirder, even less likely, given that this is true. So just be really careful here. First thing we've got to do is get our continuity correction right. The second thing we've got to remember is that we're doing a two-tailed test. Now I'm doing this using a p-value approach. You could also do it using a critical value approach, but what I'm going to work out is what is the probability of getting 15 or fewer balls thrown into slot A. I'm going to work out that probability, and then I'm going to times it by 2, because we're working with a symmetric distribution. So what we're saying is that if we see the 15 or anything less, that's equivalent to seeing something that is that far above the mean, right? That's the whole idea of a two-tail test, and they make sense only when we're working with a symmetric situation. So we're really interested in the distance from the mean. It's the best way to think about it. But we're not going to do it with 15 because we're not using x. We're not using my bar chart. we are using our approximation. Right? We want to include bar 15, which means that we're going to go out to 15.5. So this is what we're going to work out now. Okay, so we just standardise in the usual way. I'm going to take off the multiplying by 2 for now, so that we don't confuse things. So the probability of x dash being less than or equal to 15.5 is equal to the probability that z is less than or equal to 15.5 minus the mean divided by the standard deviation, which is the square root of the variance. That gives me the probability that z is less than or equal to negative 2.194. So that's that little area there. And that's the same as 1 minus phi of 2.194. Now if we wash over to the tables, we can see we've got 2.19 here, and 2.194 is the little add factor of 2. So that gives me 0.9859, which is 0.0141. So it's a two-tailed test. So we reject if 2 times that probability is less than my significance level. So 2 times 0.0141 is a little bit too big. It's 0.0282, which is bigger than 0.02. But I need to explain that in a sentence. Right? So since 0.0282 is greater than 0.02, we don't have evidence or enough evidence to reject H0. We conclude that P is equal to 1/4. Okay, so Ben, I hope that helps. There are lots of good small details to go over in there. Just remember that it is worth making sure that you're comfortable with this normal approximation to the binomial. And also the one that we've learned this year is the Poisson approx. And that's what happens when we've got NP is not bigger than 5. So if NP is less than 5, then we're talking about an asymmetric distribution. We're talking about a rare event usually. So P has to be small. And n still has to be big, and then we would do a Poisson approximation to the binomial. And if we're doing that, we don't need to do a continuity correction. Okay, keep on sending in the questions, and especially start having a look at the stats ones, because I haven't done too many videos on that this year. Thanks for watching.